Okay, things are being recorded for all of our asynchronous people. Like to welcome Kirby Runyon, who's a planetary geologist at the APL back east, and has applied to join us as a research scientist. And so I'd like to turn it over to Kirby, give a little background about yourself, and have at it.
All right. Well, thanks very much, Mark. I actually put together a slide about myself, so I might just start sharing slides now on my old personal computer here. 7 years old. Come on, Matt. All right. Can you see my screen?
It's starting to share. There we go.
Okay, you can see it. Okay, so quick spoiler. I'll be talking about what I call a panoply of solar system geomorphology, just sort of an overview of my research, recent projects I've been on, things that are happening right now. But I'd love to tell you a little bit about myself. First of all, just thanks for having me on today. I'm really excited to apply and hopefully join PSI. Obviously, you guys have a really fantastic reputation in the community, and it's an honor to be considered by you. So let's see if I can advance my slides. There we go. Okay, so who am I? Well, I'm Kirby Daniel Runyon. I got my PhD 5 years ago from Johns Hopkins University here in Baltimore, Maryland, in planetary geology. And I'm currently a senior staff scientist with APL, and of course, I'm hoping to join PSI. I live in the beautiful Ellicott City, Maryland, on right by the Patapsco River, which hopefully won't flood. One thing you need to know about me is that I'm a lifelong space cadet, but I'm someone who did something about it. I love space exploration. I went and got a PhD, of course. So space is a lifestyle for me. Sometimes I get paid for it, and so it's a combination of research and just the joy of exploring space and telling people about it. Seen here, this picture is a picture of me with some of my colleagues, mostly from Southwest Research Institute, but also APL, just after one of our reduced gravity parabolic flight experiments. That was SSW. In addition to this, I'm also a zero gravity coach for the Zero Gravity Corporation as a side gig. And I've also started a little bit into entrepreneurialism. I've started my own space exploration and space tourism consulting company, Planetary Experience Consulting. I live with my cat, Nixie, named after this small moon of Pluto called Nix. So that's just a little bit about me, and I'm going to dive into some of the science that I'm working on. Okay, so just a quick talk outline. The first section will be my research into the 4 billion-year-old impact record on both the moon and Earth. Then I'm going to transition to talking about another aspect of impact cratering, talking about ejecta emplacement, stratigraphy, cratering, and sample provenance with application to asteroids ranging from rubble pile size up to Phobos sized roughly, and also small planets, things like the moon, Mercury, and Mars. I'm also going to talk about impact cratering and ejecta emplacement on atmospheric planets, Venus, Earth, Mars, and Titan, and how the atmosphere can affect the emplacement of ejecta and the formation of cratering. I'm just going to briefly touch on some of my burgeoning fieldwork in analog geology, and I'll touch very briefly on some of the spacecraft missions I've been involved with. So let's talk about the 4 billion-year-old impact record on the moon and Earth. I got hooked on this topic 11 years ago when I was an intern at the Lunar and Planetary Institute as a graduate student with David Kring. And I was hooked on this question of, did the late heavy bombardment as a spike in impact reflex, did that actually happen, 3.8 to 4 billion years ago? And I think one of the reasons that's so interesting to me is it's a testable hypothesis. We can actually, the moon is the closest planet to Earth. Yes, I called the moon a planet. I'm very inclusive that way. But one of the really interesting things is, of course, the moon is the only witness plate. It's the only geologic record that records the activity at 1 AU from the sun. And so if we want to know what happened on early Earth at that time period, we have no choice but to go to the moon. Fascinatingly enough, that 3.5 to 4 billion years ago, maybe even a little further back, is of course when life first emerged on Earth and got a toehold. And while I'm not an astrobiologist, I'm fascinated by astrobiology, and I want to apply my skills as a geologist to kind of form some of those boundary conditions on what the environmental boundary conditions on Earth were like with regards to the impact reflux when life was making that mysterious step from complex organic chemistry to what could actually be called life. So along those lines, I've published 2 papers to date on this topic. What I have been doing is doing geologic mapping on large basins on the moon, and interpreting the geologic subsurface as a way to constrain where future missions should go, whether they're crewed or robotic, to do age determination of impact melt deposits. And I feel very lucky and very fortunate that just very recently I was awarded a Lunar Data Analysis Program grant that just kicked in the beginning of this month, right as the opportunity to come to PSI presented itself. So I barely started on this grant at all, but I do have this publication record on it. So skipping back here. Okay, so the strategy with this very detailed geologic mapping in very small areas and interpreting a geologic cross section, the strategy behind this is that these large impact basins, whose ages, if we could get at them, record the timing when they formed, and can then therefore let us test whether everything happened all at once in the truly lunar cataclysm, or if it was more spread out over time. These are old enough now; they're superimposed with large, complex craters. And one of the things we can all remember from graduate school is that when you have a complex crater, subsurface stratigraphy gets uplifted in the central peak or the peak ring, and it can be exposed at the surface. So if you have a geologic desire to go down stratigraphically, when it comes to central peaks and peak rings, that means you have to go up topographically, and that's sort of guiding the philosophy of this research. So you know, there's 42 large basins on the moon, 200 kilometers diameter or larger, or 42 known basins, not including the South Palatinate Basin. And so basically we just got to start going one at a time, picking them off, picking a large basin, finding out where you could find pristine exposures of impact melt, and then think about, you know, sending a mission there. So in the current research I'm presenting my work on the Smithy Impact Basin. Maybe others pronounce it Smithy, I suppose. It's a pre-nectarian crater it's on the far side, but it's pretty close to the near side, far side boundary on the moon. Part of the interior basin is flooded with Mare basalt from Mare basalt volcanism, and other aspects aren't. It's also really beat up. I mean, people still have arguments over where the peak rings are and where the true basin rim are. So it's not that well constrained, although topography data and then gravity data from Grail have helped constrain that. One cool thing about Smithy is that it is roughly the same size as Oriental, the largest multi-ring basin, or the youngest multi-ring basin on the moon. And so we can sort of use them as a bit of analogs for each other. That's not quite perfect because there have been oblique impacts involved and things aren't quite circular, all that. But we can generally use the geologic context of Smithy and start honing in on where a future mission could find impact melt from the Smithy forming impact. This was both a geomorphological structural geology and an infrared remote sensing spectroscopy exercise, working with Ben Greenhagen on the Diviner instrument, and Dan Moriarty at NASA Goddard, who is an M-cubed wizard, having done his PhD with Carly Peters. And so this is a plagioclase fraction map of the area. You know, when you look at Smithy Basin and you're like, okay, I want to get to some stratigraphy that was uplifted that preserves the impact melt, your eyes go to Knepper crater. It's a beautiful complex crater with a shining central peak. But there's also these smaller complex craters further to the south. One of the things we note about the Smithy Basin is that a lot of the superposing craters are floor fractured craters. Lauren Joswiak has done a lot of work on this. In fact, her entire PhD at Brown with Jim Head was focused on mapping floor fractured craters, classifying them, and coming up with a mechanism. So basically, we're seeing the effects of a lot of plutonism, a lot of magmatic activity, acting like a piston on the crust of the moon and kind of pushing it up and fracturing it. And so there's a lot of vertical dynamics going on here, and it's a fun place to try to tease out the natural history here. So I worked with a PhD student at Johns Hopkins University, where I have a visiting scholar position, no exchange of funds. They basically give me a key and let me show up and talk to them. But I did this work at the beginning of COVID with a PhD student there, Lyle Nelson, who recently became a professor in Canada. And so working together, we both geologically mapped this area here, really honing in on a couple of the different Mare basalt units here, the ejecta deposits, we only mapped craters larger than 20 kilometers in the area. And combined this, worked with Dan Moriarty to look at the composition anomalies across here. And so we mapped out several units here, and then we interpreted a geologic cross-section. I'm finding I have to click a few times to advance slides. There we go. And so if we follow that A to A prime there, we interpret the interior to have, 7, 8, 9 kilometers worth of impact melt from the Smithy forming impact. But really, once you get outside there, there's a lot of highlands, of lunar highlands contamination that's probably not from the Smithy impact melt. There is this thing outside the Smithy peak ring we've sort of termed the splash zone. I don't know if other people use that term. It turns out probably actually the central peak of Neper crater isn't the best place to try to find impact melt sheet that you could age date. But it turns out that the humble Schubert C crater there, even though it's surrounded by Mare basalts, it seems to predate the Mare basalt floods, and there does seem to be an outcrop of what is likely to be Smithy impact melt in that region there. Not content with just characterizing it, I wanted to come up with some notion of how one could actually go and test this hypothesis on a future mission. Someone could land a robotic spacecraft or even a crewed spacecraft. Wouldn't that be exciting? On the central peak of Schubert C crater, potentially at landing option 1 there, kind of near the center of the screen. The great thing about trying to sample outcrops and boulder fields, which we've identified here on this map, is that mass wasting is your friend here. The mass wasting is constantly exposing fresh, relatively unspace weathered, ungardened, unimpacted, since the formation at least, a material that could be suitable for age determination, either in situ or in return. So that's where things are at right now. I've published 2 papers on this, just starting a new LDAP that I'm hoping to get transferred to PSI here pretty soon, and really go to town with ArcGIS, doing some mapping. So I'm going to leave this at this portion right now, and I'm going to go on to another area of my research. And that is ejecta emplacement, stratigraphy, cratering, and provenance. If I haven't said it yet, but hopefully it's clear that impact cratering is really the most common surficial geologic process in the entire solar system. It's everywhere: moons, small bodies, planets, even giant planets. Let's see. I've done some work in this, including a big chunk of my PhD, where I published with Olivier Barnouin, and that was back in 2018 when this paper got published. I've also had a number of abstracts come out since then on there, and happily enough, a couple years ago, I won a solar system workings proposal that will hopefully also get transferred to PSI. And this is looking at ejecta emplacement specifically on small bodies. So I'm going to I'm going to focus more on small bodies here for a minute. But by way of motivation, the Hayabusa spacecraft actually carried out an artificial impact experiment on Ryugu. And you can see this movie here. Hopefully you can see the movie playing of this ejecta curtain forming on the limb of Ryugu there. And then off to the right, of course, this picture is just a couple of weeks old when APL working for NASA slammed the DART spacecraft into the asteroidal moon Dimorphos. And then the Italian Space Agency spacecraft LICIACube captured this incredible image of this very surprisingly, at least to me, filamentary ejecta coming off Dimorphos in the upper right there, while the primary Didymos, sitting down to the lower left there. So I'm interested in ejecta emplacement, both on worlds with very low gravity and anywhere there's a solid surface. Of course, so this is a video from NASA Ames. This was on the Science Channel. This is one of Pete Schultz, famous experiments. I focus, increasingly I'm focusing on the cratering aspect itself, but traditionally I've just focused on the ejecta curtain, this wall of material that's getting excavated from the crater you can see coming up here. Some of the motivation also comes from things like OSIRIS-REx, where the TAGSAM instrument got unexpectedly buried in the surface of Bennu. When it comes to cratering, you can see some craters here. You can basically model these rubble pile asteroids as viscous liquids more than like what we would think of as a rock pile. I mean, the spacecraft just kept sinking and sinking in until the timer on the spacecraft was like, that's been long enough. Let's fire some thrusters and get out of there. Sorry, I apologize. This slide seems a little bit out of order, but that's more of the context that I want to apply my craft. And one of the ways we do this is with this giant catapult at APL. And by the way, if I do come to PSI, and hopefully that works out, I still have colleagues, co-Is at APL. I should have no problem gaining access to their planetary impact lab facility and the ejecta catapult. This is basically a human-sized mousetrap. It's a roughly 1 square meter steel plate that's got this hinge and this pivot point. You can load it up with gravel, let it fling, and you can simulate an ejecta curtain without having to first simulate the crater. And so it spares you from having to bury explosive charges and blow up people's lawns. The idea behind this is that you've got a catapult sitting outside of an imaginary crater, and you're just simulating, where I've marked simulated area, some portion of that ejecta deposit. What this looks like is here in this video. Hopefully you can see and hear it. I don't know if you can hear it at all. This is literally just colored aquarium gravel. We set up high-speed cameras. We capture its ejecta emplacement. We can do particle velocimetry to get the velocity distribution of the ejecta. And if you play it back at 1200 frames per second, or if you play back that footage at regular speed, you get the slow motion here. We can even get into the geomorphology of this dynamic situation here, where you've got this, what I call a dynamic deposit of ejecta that trails along behind the ejecta curtain. I mean, this goes back to this Oberbeck paper from, I think, 1975, where he showed that, or he hypothesized, whatever, put forward, that ejecta continues to slide outward from the crater a long ways after an ejecta curtain has landed. A lot of simpler models treat ejecta as this static blanket that it comes out of the crater, it flies, and then it lands and it stays put. But in fact, it's a very dynamic environment that can lead to a lot of abrasion, erosion, mixing, and it's a crucial geologic process that I believe is necessary to interpret remote sensing images and field data. One of the surprising outcomes from our ejecta experiments, and hopefully you see this playing here, this is an experiment where we deposited this red kind of coarse sand. It was actually like coarse clay, almost like kitty litter, cat litter. Let me see if I can get it playing again. But this red ejecta deposit on top of this blue regolith simulant, they're identical except for the color. And you can see this linear shear profile. If you watch any given grain at depth, you can see where it's getting displaced downrange away from the catapult or away from the imaginary crater as it forms. And being able to look through the clear side of this acrylic into our target box here was really crucial in being able to infer some of the structures we've seen at terrestrial impact craters. This is Reese impact crater in Germany, where aspects of the ejecta deposit, the Bunte Breccia, have been excavated. People see evidence of the shear detachment fault, where whole layers of stratigraphy have slid on each other. There's blocks with striations on there that are oriented radially to the crater. So between the striations and these lateral displacement faults, there's a lot of evidence that the deposit of the Bunte Breccia probably caused a lot of subsurface shear, and that shearing can probably extend quite deep underground. We also saw, people talk about impact gardening all the time, but there's not a lot of experiments to show what that would actually look like. We showed evidence of where exhumation happens, implantation happens, basically everything we think of with regards to gardening. Now, this is all well and good for talking about a laboratory setting, but are we actually simulating anything real that happens in nature? That's where scaling comes in, being able to take what happens in the speed and size regime and the mass regime in a laboratory and scale it to natural conditions. So these types of plots go back to a lot of Vern Overbeck's and Pete Schultz stuff from the 70s and 80s. And earlier, where if you plot these two variables next to each other, this thing called the erosive efficiency, it's how much mass you deposit divided by how much mass gets eroded, or how much mass your impactor has combined with the excavated mass of your impact crater, and you plot that in log space as a function of basically the inverse Froude number. It's this ratio of gravity, length scale, and the square of the velocity. And that allows you to non-dimensionalize. Now, one of the things that I'm kind of crazy about, because it's so weird, is these purple X's here. These are data taken in the 1890s by dropping lead weights off buckets into buckets of water from a ladder. and they fall on the same power law curve as experiments done in the upper left corner there at NASA Ames at 7 kilometers per second simulating impact cratering. The fact that these scaling laws exist over such a decades of changes, just, it's amazing to me. I don't, it's kind of a mystery to me why nature is like that, but there it is. The initial laboratory ejecta experiments seem to plot down here in the lower right. There's not enough there to say if it follows a power law. Is this even worthwhile if it's not a power law? I think even if this doesn't scale, I think there's still something to be said in terms of qualitative interpretation of the range of geologic conditions you might expect. Now, in this parameter space, look at, this variable here, gravity, length scale R, V squared. In the laboratory, you can twiddle your knobs on the physical size of your ejecta curtain, and you can twiddle the knobs a little bit on the velocity, but you really can't twiddle the knob on your gravity. You're stuck at 9.8 meters per second squared, unless you cheat. And I'm not going to admit to being a cheater, but this is one way to get to change the gravity knob. We proposed and won this SSW to do ejecta emplacement experiments in reduced gravity on parabolic flight. This is GForce One, the website go0g.com if you want to book your flight. And so we did our first set of experiments this last December with my crew from Southwest Research Institute and APL. And here's what it looks like in flight. This was our aircraft flew in a series of parabolas, of course, and we did 30 parabolas. The first 10 were Mars gravity, 3.62 meters per second squared. Same as Mercury gravity, by the way. Our next 10 were roughly lunar gravity, 1.62 meters per second squared. And then our last 10 were zero gravity, microgravity, milligravity. It was a little bumpy, but there were definitely periods of zero gravity in there. But we were interested in like centigravity, if you will, the gravity level on asteroids. And so this still frame here shows this orange ejecta curtain coming off the catapult right here, which is has a pivot on the bottom and it's attached to springs. There's the sand tray right down here, and then we've got GoPro cameras tethered right here, looking from the top down, and a perspective view over here. While we use an accelerometer on Todd Smith's cell phone, we have since bought real accelerometers and data loggers, but the cell phone seemed to give pretty good data too. In terms of more laboratory methods, here's what the setup looks like in an aircraft hangar. We went down to Florida in December, which was nice. And for those of us who live up north in Maryland, and so there you have that. A lot of fun getting ready for flight to do some experiments. This is kind of in the weeds. Each experiment used 1 cup of colored sand, 0.9 pounds. We use different spring constants for different gravity levels. And then, of course, here just a better view. Here's a green sand ejecta curtain with from the stratigraphy of some previous experiments, orange and blue from previous experiments here. And next slide, I'll just show you a cool video of what this actually looks like. Hopefully it plays okay.
It is pretty cool.
Here's what some of that looks like. I think that was Mars gravity or moon gravity. Sorry, these pictures are getting a little gratuitous. Here we go. There's a fun shot. Okay, great. And we measure and all of the data is in the form of video, and we can use the pixel scale. We can calibrate to physical size. We know the frame rate, so we can get velocity, and so we can get the physical size of the ejecta curtain as it deposits. We can get how far from the catapult it is, and we can get velocity. And in fact, in this multi-step process to get velocity, we put in some digital tracer particles, and then we have software track the tracer particles, and we get speeds several decimeters per second. Now that and of course, we've also got the accelerometry data, so we know the gravity level there, and that allows us to begin to non-dimensionalize these results and start to think about some scaling laws. And in fact, if we plot these data on our old friend, this plot here with erosive efficiency or cratering efficiency as a function of inverse Froude number, we haven't gotten to measuring the M over M yet. We're still very much in data analysis, but we are starting to get inverse Froude numbers around 1. compared to much smaller numbers for hypervelocity impacts and values of around 0.02, 0.04, close to 0.1 for for larger fixed ground-based catapult results. So the data seem to suggest so far that that at least lunar and Martian gravity kind of plot down in here. Our last flight was not, we weren't able to get the amount of erosive efficiency, and so we have another flight lined up for this coming spring where we're going to change a few things with the experiment and try to get that erosive efficiency. So, oh yeah, the next slide speaks to that. So we need some higher resolution data like we have for the fixed base catapult here, so that we can, we just didn't have the resolution here. So we bought some new lenses. We have some better ideas where to place the cameras. I think the next one will be good. We're also not going to use sand. One of our lessons learned was, especially looking at the surfaces of asteroids, a carbonaceous chondrite, the surface of a C-type asteroid, the rocks have a surface compressive strength of like a few megapascals. Turns out chalk, like literally sidewalk chalk, has the compressive strength of a few megapascals. And so we found that probably a better rubble pile asteroid simulant is to take chalk, hammer it with a hammer, which will kind of basically give you a power law size distribution of grains, and then you'll get big stuff, small stuff. It'll be a bit more natural. And I think this will be a better regolith simulant for our coming flight in the spring. So yeah, so flight next spring, we'll get more data here and learn more secrets about the universe. Now, let's go on to more crater ejecta stuff. Okay, so over the course of the last year, I was fortunate enough to win an IRAD at APL. Thank you, APL, and sorry, to look at the atmospheric effects on impact cratering and also ejecta emplacement when you have a thick atmosphere to worry about. And I've worked with Olivier Barnewin, Noam Eisenberg, Carolyn Ernst, and Angela Stickel at APL over this. And really my motivation for looking at Venus is, hey, come on, Venus is so hot right now, so I could not do it. We've got two US government missions coming up to Venus. MIT and Rocket Labs are doing the first, to my knowledge, private planetary mission in a few years. And that's going to be a cloud nephelometer to look for signs of life in Venus's clouds. And then, of course, Europe is sending Envision to Venus. So we've got, so Venus is hot right now, literally and metaphorically. So the question we're trying to address is, how is impact crater morphology, morphometry, and ejecta affected by atmospheric pressure? And how could this be used as a geologic tool to help us probe Venus's past? And it's not just Venus, but it's really every planet with a thick atmosphere. This image of Mars here, I think this is Baccalaureate crater. Rampart ejecta is very common across the surface of Mars. You can get multiple layers on top of each other that forms these beautiful lobes, this lobate morphology here. There's similar lobate morphology in Venusian ejecta, seen here in this Magellan radargram. There's probably a distal rampart. By rampart, I mean a topographically raised distal ridge on downrange of this. For Mars, people often attribute this result to basically a muddy subsurface, or there's ice that gets melted mixed with the regolith in the heat of an impact. And then you've basically got a Bingham plastic that flows across the landscape. And as soon as the shear stress on this Bingham plastic ejecta falls below some yield strength, it stops acting like a liquid, and it all of a sudden seizes up and starts acting like a solid. And maybe that's where you get distal ramparts. There's also evidence on Titan for possible lobate ejecta. It's really hard with the Cassini radar and IR images, but there does seem to be some lobate ejecta there. Fortunately, the APL NASA Dragonfly mission in the 2030s will land and then take off, and then land and then take off, and land and take off around Selk crater and the ejecta field around Selk. And even though it's more focused on the organics and the sand dunes, hopefully we'll get some ejecta morphology out of that as well. So this research into atmosphered planets is broken up into cratering and ejecta, and I'm going to talk about the cratering first. Yeah. So there's not a ton of at least recent work on atmospheric effects of cratering. There is this old forgotten paper by Pete Schultz from I don't have the date on here, but it's in this obscure journal that nobody's ever heard of, and where he kind of talked about some of this. But like, people aren't doing this, so I figured it was ripe, and APL was generous enough to give me an IRAD to start looking at this. One reason you might want to do this, and I touched on this earlier, is that you can use cratering and ejecta as paleo-atmospheric proxies, as well as just understanding, the basic science of how ejecta modifies the landscapes of planets with atmospheres. And then, of course, use your imagination. You can apply this to exoplanets too, if you're so inclined. On Venus and planets with thick atmospheres, the ejecta curtain can be modeled as a plate that pushes on the mass of air. Aspects of the curtain have certain amounts of permeability, especially as you go higher up in the ejecta curtain. You can get air coming through and then forming these vortices behind it. These helical vortices may be responsible for some of the ejecta morphologies, like this lobate morphology, or the layers, or the ramparts. And so disentangling the different geologic processes that give rise to these landforms is important for those of us who think this is interesting. I think it's interesting. So the methods we employed in this pilot study, and it's just a pilot study, is we used the APL Planetary Impact Lab. The gun, the current impact gun can get up to 250 meters per second, not quite hypervelocity. I know they're working to get a few kilometers per second. We've got a vacuum chamber. It gets down to about 7 torr, so like Mars pressures. But instead of making a Venus environment chamber, which sounds scary and terrifying, instead of having a Venus environment chamber, we're like, well, really the thing we need to test is for when we have ejecta that can be easily entrained in an atmosphere, or when we have cratering target material that can be easily entrained in an atmosphere. And so rather than pumping up a pressure chamber to 90 bars, we use very fine-grained volcanic pumice from Idaho, which is very, very fine. It's a very fine-grained powder. And so you can come up with a dynamic similitude parameter where the weight of each individual grain, where you get the weight to drag ratio to be the same for the pumice on Earth as a several decimeter size block would be on Venus. So that's sort of our scaling parameter there, is the weight to drag ratio. And then we use a 3D photogrammetric scanner to get very precise topography of the crater and the ejecta. We also use this laser sheet that helps you see it a little bit better. I think this is a video that plays. Yeah, okay, so this is just a video on loop showing one of the craters we did in very fine-grained pumice. It was when we did this in vacuum, not a huge surprise. We got a very normal looking impact crater with roughly 10-to-1 aspect ratios in diameter to depth. But so this is sort of our control, doing it in vacuum. This is our control experiment. The exciting experiment, the thing we're testing, of course, is the effects of an atmosphere. So we use Earth's ambient 1-bar atmosphere in the same stuff, and we get this. It's a little hard. This image isn't quite as clear. I apologize. But hopefully you can see it's much more muted in its lateral extents, and it's much deeper, at least relatively speaking. And there's like this weird pit in the bottom. And when we extract topographic profiles using the photogrammetric 3D scanner, we see that the vacuum crater plotted in these blue points here, not surprising, looks like a normal crater. You got this nice uplifted rim right here. But in atmosphere, it's relatively way the heck steeper, very steep, almost like a compressive crater here. It's got a depth to diameter ratio of 0.4. Like that's just not normal, folks. So so there could be something going on with how thick atmospheres affect cratering. This forms the basis, the nucleus of a grant proposal that I am working on right now, and I hope to submit through PSI. As a quick aside, one of the nuisances, let me turn down the volume here.
Wow. Wow.
As we were pumping the vacuum chamber down to pressure, we had this pumice. Oh, by the way, it's super fine. It's 27 microns in diameter. This stuff is powder. It almost sloshes like a liquid in a bucket. I'm not used to seeing this stuff. But as we pumped down to pressure, once we got down to about 10 torr, it started boiling and erupting and geysering. And it really destroyed our ability to do an impact cratering experiment in this. We had to repressurize level it all out. And by that point, it had degassed. We pumped down again and it behaved itself. But I thought that this might be really cool to think about, geysering on Mars, Triton, and Pluto. So if anyone wants to put in a proposal for some experiments and modeling and mapping related to this, let's chat. All right, so I'm easily impressed, folks. Okay, let's now transition to talking about not just cratering, but also ejecta when you have a thick atmosphere. So here's Olivier packing down the 27 micron pumice onto the ejecta catapult. And then this is and then on the right, we have a still video frame of what it looked like. You recall before we had like this nice, well-behaved wall of gravel that was just inclined 45 degrees to the ground, and it behaved itself and everything, and all was right with the universe. Well, this is the roughly equivalent thing when you've got a very thick atmosphere and an ejecta deposit. We've got this turbulent dust cloud. We've got these ejecta clumps at the front of this, and then you see these streamers behind it. You can also see these clumps in slow motion flatten out and then spread down range. And if you've ever watched slow motion video of nuclear explosion tests out in Nevada, you can see this, like the Sedan nuclear crater and the Schooner crater. You can see these like bombs of ejecta coming out with streamers behind them, and then they impact and spread out. So one thing I would love to do in the future, as another throwaway aside comment, is I'd love to go out to the Nevada National Security Site and do some nuclear crater analog field work there. And they've been recently opening up to NASA funded scientists. So that could be a possibility. Here's a video of what that looks like, the pumice on the catapult. This, yeah, okay, great. Now, okay, I don't know if you can really see it, but we got this incredible lobate ejecta deposit. Let me go out to the next slide here. All right, spend some time staring at this gorgeous ejecta deposit. The ejecta deposit was, came from left to right here from the catapult. Look at these beautiful layers. Look at these beautiful lobes, this incredible lobate morphology, and look at these just stunningly beautiful ramparts in the distal margins of these lobes here. This is completely dry. This is just very fine-grained pumice that's subject to the atmosphere. And look how reminiscent it is of Mars. I'm not saying that this is the same process that made the ejecta deposits on Mars. What I am saying is that you can make this morphology without any water, without any lubricating fluid other than air or the ambient gases. You can get this. So hopefully these types of experiments will help us better interpret the sorts of things happening on Mars, and especially on Venus and also Titan. And in the case of Venus and Titan, in the coming decade or two, we're going to be getting a whole new ton of data to allow us to test these hypotheses. When I put in my IRAD proposal at APL, I said, look, for how much time it takes to get a proposal funded based on when these missions are going to be flying to Venus, we got to start doing lab experiments right now to start constraining the processes so that we can correctly interpret what we actually see when we get there. So in terms of application to Venus, I stole this slide from my recent presentation at the Ancient Venus workshop just like a month or two ago. The crater depth to diameter ratios may indicate a thinner atmosphere than present at the time of crater formation. So, Venus's hellish atmosphere is probably only about 1 billion years old. And if there are any craters older than 1 billion years old, again, TBD, there's only 900 craters on Venus. They're all probably pretty young because Venus likes to turn itself inside out. One of the things we need to look at is how much can we probe into Venus's environmental past using crater morphometry and experiments and modeling, of course. And this, of course, assumes you've had negligible geologic infilling and negligible relaxation of the crater. Okay, well, more spacecraft data, maybe even buried craters. Would we be able to discern the presence of buried craters or partially buried craters that are just missing from the Magellan and Pioneer and the Soviet Venus data sets? Ejecta runout could vary as a function of atmospheric pressure at the time of emplacement. And I'm currently writing a ROSES proposal, like I said, on this. Probably going to use, and I've already talked to Dan Durda at SWIRI about doing some experiments at Ames. He's got a ton of experience with that. I'll have colleagues at APL, but would love to talk to some PSIers about what we could do with this, like maybe put in a modeling component. I'm not a numeric modeler, but it'd be great to work with someone who is. Okay, so I'm gonna that's my talk. I also just want to cover just a dump of some other activities that I've been involved with that are talks in their own right that I wasn't going to subject everyone to. And that is that I have, in the last year, been the planetary science lead for the Interstellar Probe APL mission concept. I really like occupying, I love the science, but I also love occupying that space between scientist and engineer and figuring out the ConOps and making a case for exploring the 130 dwarf planets beyond Neptune. Dwarf planets are the most common type of planet. Chances are, if you're a planet in the universe, you're a dwarf planet. I'm also a science team member on New Horizons and the New Horizons Kuiper Extended Mission. PI Alan Stern has already confirmed that my funding will, I can take that with me to PSI, should you choose to have me. I've also had the opportunity to teach on 2 occasions at Johns Hopkins University. I think most people on here know that Johns Hopkins APL is a separate campus from Johns Hopkins University, even though they are connected. I hope to maintain my no transfer of funds friendly, relationship with Johns Hopkins University main campus, their Earth and Planetary Sciences department, same department I got my PhD from. But I taught a seminar class called LEAG, Lunar Exploration and Analog Geology, and that was an undergraduate seminar at JHU. And we read 3 different types of papers. We read, we read a lot of papers over the semester, but they were on lunar geology, they were on analogous terrestrial geology, and they were on how you do exploration on the moon, both robotically and with humans. So it was looking at a lot of Apollo literature and a lot of desert rats literature and some survey literature as well. The year before that, I led a group of undergrads on an analog geology moonwalk, or fake EVA, in the Sima volcanic field in California right before COVID. So we had this phenomenal, we walked amongst the lava flows of these beautiful cones and flows just east of Baker, California. And we simulated the kind of concept of operations that astronauts have to do when you're describing something on the moon. I very recently, just in the last few weeks, led a Venus science definition team for a small mission concept architecture. The architecture was, say you had 3 or 4 probes, landers, that could last for about a week on the surface of Venus. What kind of science would you prioritize if you did that? So we wrote up basically a white paper about that. Not sure what we're going to do with the white paper. It's not quite a full paper, but it's more than an abstract, so I don't know where it fits. It's in the gray literature at the very least. I am coming off of being a co-facilitator for the in situ resource utilization focus group of LSIC, the Lunar Surface Innovation Consortium. So I've been working, APL has been running LSIC for NASA's Space Technology Mission Directorate. And so I've been able to network with a lot of companies, helping them understand the moon and how the moon basically forms the requirements for their engineering for, in our case, in situ resource utilization, ostensibly, especially mining out oxygen and aluminum from regolith, not so much the water from PSRs. We're not there yet. We've got more prospecting that needs to happen. Just a couple months ago, I was fortunate enough to go to Caltech, to the Keck Institute, and got to be a Venus KISS workshop participant for a workshop on Venus science enabled by human proximity. And I'm very proud of our group's white paper that we just released. And it's not a peer-reviewed paper, but it's a good paper, and it's posted somewhere. I'll have to check if anyone wants to read it. I'm very proud of it. It's on the KISS website, at the very least, at Caltech's website. So turns out humans flying by but not landing on Venus can do a lot of science with real-time teleoperation, and you can test a lot of stuff before humans ever go to Mars. I'm also really interested in the Artemis program and the geology. If the call ever officially comes out, I'm a co-I, or I'm planning to be a co-I on one of the Artemis 3 geology teams. I also applied, was not selected, and plan to reapply to do desert rats, where NASA has funded field activities to simulate lunar exploration. And this last December, thanks to an award I got at APL, it's basically a different type of IRAD. I got to go to Johnson Space Center and the Lunar and Planetary Institute for what I call mission control boot camp for scientists. It's how to work and function and especially communicate in a mission control environment as a planetary scientist, as a lunar scientist. So I'm very keen on science enabled by astronauts. And I've also been in stuff with probably some other stuff I'm forgetting at this point. So to sum up, I probably should have put this slide before the previous slide, but ejecta emplacement affects the subsurface, and understanding its emplacement is necessary to interpret samples and other geologic units. Mapping certain lunar areas will help constrain Earth's early impact environment around the time of life's first emergence. Analog geology, astronaut-enabled science, and parabolic flights. I love parabolic flight. I do it both in my science and for fun, and this what actually literally is space tourism. I've got 16 parabolic flights under my belt now. I just passed an hour of cumulative time in weightlessness, and it is such an addictive feeling. So I want to keep doing that both as a zero gravity coach and as a planetary geologist. I'm on 2 PI grants, and there are 3 more grants that I'm either the PI on or co-I on that are in various stages of development that I hope to run through PSI if you will have me. And if you'll have me, I very much am looking forward to joining you in your community. So thank you very much for your kind attention.
Thank you very much, Kirby. Any questions for Kirby?
This is Deborah Domingue. Yes, I do have a question for Kirby.
Hi, Deborah.
Hi. So I was really intrigued with your experiment that showed the lobate scarps, the lobate ejecta. And I was wondering if you could say something about, the formation of peak rings and showing flow features off of peak rings in terms of a dry environment versus a volatile environment, if that you have any insight into that.
I have not thought about that, Deborah. So Deborah, I think that's a wonderful question. I have not thought about that. I've been focusing more on the ejecta and then the formation of simple craters, at least because in the lab, simple craters are what we can form. Complex craters are a lot harder to form. If you have any insights into modeling or experiments that could look into gas versus fluids, how that could happen, I'd love to talk more. I think that's really fascinating. Wow, off the impact cratering mechanics and all the structure and uplift, it's a little bit outside what I normally do, but that's a really interesting question. And I don't have a satisfying answer off the top of my head, but I'd love to think about that more.
Okay, thank you.
Oz.
Hey, Kirby, great talk. Love the enthusiasm.
Thanks, Oz.
Just a quick question. That surprising filamentary structure for the dimorphism. I mean, are there any theories about, that people, I don't know, just put out in the wake of the impact?
Great question. I'm not on the DART team. I did, however, just go to a public talk last Friday at the Cosmos Club in DC, where Andy Chang and Andy Rivkin spoke about it, and they were very coy. But one idea is there was something like 30 kilograms of xenon and 10 kilograms of hydrazine, or maybe the reverse, still on board the spacecraft. So you're volatilizing a lot of hydrazine and xenon right now. That might have something to do with it. I'm sure the DART team is looking at that, but there's like 30 papers being prepared right now. So maybe the answer will be buried somewhere in there. Right. When it comes to that filamentary structure, your first instinct, or at least mine, is to think, well, that's something you get when you've got entrainment in a gas, in an atmosphere. Seeing that in vacuum, I find surprising.
Right.
Maybe that's a transient atmosphere from the vaporized spacecraft propellant that's causing it. I don't know, but that's a really interesting thought. I would be really curious how much of that ejecta re-impacted the surface of Dimorphos versus how much escaped. And then of the stuff that re-impacted, one of the things that I'm really interested in with my parabolic flight experiments is to look at the degree of surface-subsurface mixing. If you've ever taken a class in hydrogeology, there's this thing called hyporheic exchange between surface water and groundwater. And like in my mind, I've got this analog of ejecta and then the regolith, because the ejecta, 2 seconds ago was regolith, and seeing how that mixes. So I'd be curious how that filamentary structure, or maybe we don't normally get filamentary structures when there's impacts. I don't know. I think there's a lot of I think the parameter space for having fun doing experiments and modeling and publishing is quite large.
Very cool. Thanks.
Kirby, it's Mark. I just wanted to say about the DART impact, that a lot of our expectations are based on looking at things as a spherical cow. And
Yep.
so we're used to these nice smooth things, impacts in there, uniform ejecta and all that. You know, what if this is impacting into a very large boulder collection of things, so that the ejecta is actually running into shit, and so it just represents maybe things that are blocking ejecta.
Yes. Okay. Yeah. Mark, I love that. And if I could just riff off that, let me just riff off that idea. You know, Olivier Barnouin has done experiments where the impactor is on the same order as the size of the target grains you're impacting into. And that was kind of the case on the surface of Dimorphos, because the spacecraft was the size of some of the blocks it was impacting into. And it wasn't this nice, fine lunar regolith. It was a lot of coarse stuff. And so probably this filamentary structure, to get back to Oz's question then, could very well be the results of really coarse grains that are maybe kind of fragmenting. So, you know, just to speculate a little bit. Yeah, it's probably because it's really coarse, Mark. That's a good point.
Just a thought.
Yeah, I like it.
Other questions for Kirby? I did have one thing I want to bring out. I would love to have a little short clip of your bubbly pumice type stuff.
Yes.
But because I saw that about 10 years ago here at PSI, when some fine material was for an impact experiment was being evacuated. Same thing as you're doing. It was being done by Jim McElwain, who's now a professor over at the University of Durham. And I'd love to take a little clip from your thing and just send it to him, and say, hey, did you do anything more about this? You know, do any experiments about this, and hook them with you.
Yeah, that'd be great, Mark. My understanding is most impact cratering scientists think of it as a nuisance to have that boiling target material, but one person's noise is another person's data.
We're all standing around it just going, wow, this is really cool.
Yeah. But like raniforms on Mars, plume deposits on Triton, maybe these are related. So
yeah.
Amanda has a comment. I completely agree, Amanda.
We should do it as part of the retreat or something.
Now there you go. You know, we like to do like a field trip type thing.
Yeah, exactly.
Oh.
For research.
Yeah.
So I will say a little bit on my entrepreneurial side stuff. I've run this by Mark. There is no conflict of interest. Me being a zero gravity coach and also doing NASA experiments on there. It's just a fun laboratory environment. But I am working with the Zero Gravity Corporation for what I'm calling the Planetary flight experience for next spring, where people can have a nice dinner the night before, hear a presentation on the planets and the moons, which are planets, and the gravity levels that they're going to be experiencing the next day. And then we do 3 parabolas of Mars/Mercury gravity, 3 parabolas of Earth's moon and other large moon gravity. And that's all a pretext to talk about Europa and Titan and all these other places. And then we have 9 microgravity parabolas, which are similar to rubble pile asteroids. So that's a little bit on the entrepreneurial side of things. That will be outside of my PSI hours, but
that sounds neat. Hopefully the customers don't throw up their nice dinner from the night before.
Yeah, sometimes that happens.
No, I think it's super fun.
Thanks. Yeah.
Any other questions? Okay, well, thank you very much, Kirby. This was a great talk, a lot of fun, and we'll be in touch.
All right, very good. Thanks so much, everyone. Great to talk to all of you. Thank you.
Yeah.
Bye.